Hello and welcome to the third installment of Precision Medicine Pulse, your weekly news digest about the precision medicine industry. So, in today's episode, we're changing up the format a little bit. We're going to keep things a little bit more interactive. If you're listening to this on Spotify, it might be useful to look at the screen because there's going to be a little bit more visual stimulus here. I'll be sharing my screen as we walk through some of the science and walk through some of the AI and data stuff that's going on in the news today. But because I'll be going into things in a little bit more depth than what I've usually done, this means that we're not going to cover as broad of a range of news stories that happen during the week. However, we're gonna target the main two things, or the two things that have jumped out to me as being the most interesting, and we're going to go into them in a lot of detail. The first story that we're going to talk about is related to a company that's near and dear to my heart because they have a manufacturing facility in my hometown in Ireland, in Limerick. It's one of the biggest factories in Limerick, and it's Regeneron. So I am biased towards Regeneron, but they're in the news this week for for a good reason. Um, they've got a gene therapy that's targeting patients with a specific rare genetic deafness. Specifically, the target here is due to genetic deafness that's due to a mutation in the otoferlin gene, which causes sound to not properly get transmitted to the cochlear nerve. Um, when you think about your ear, how do you hear stuff? Well, sound waves come in through your ear canal. If you're listening to me right now with headphones or in a speaker, sound waves are passing in through your ear canal, hitting your eardrum inside in the middle ear. And you've got a bone here that when the eardrum vibrates, it vibrates this bone, which in turn vibrates the cochlea, which is like this snail thing inside in the inside of your ear. It's shaped like a snail. And that cochlea then, in theory, if everything's working properly, is able to transmit sound waves to your um, vestibulocochlear nerve, if I've got my Latin correct, uh, which in turn transmits the signal to your brain and you can hear stuff. The problem with people who have this particular genetic mutation is there's a disruption in the transmission of signal between the cochlea and the cochlear nerve. So you have there's these hair cells that transmit the signal from the cochlea to the nerve, and they're disrupted. They're not working properly due to this mutation. And Regeneron's targeted treatment, it there's a surgery that puts let's say an inert or a non-dangerous virus into this inner ear, and the virus has a payload of otoferlin genes that are functioning correctly. And the idea is that it spreads, and as it replicates inside in your inner ear, it's able to offset the effects of the genetic mutation in the otoferlin gene, or at least that's what it's meant to happen in theory. And in practice, Regeneron are just after their phase two trials, phase one and two trials for this treatment that they've designed. There's a couple of other companies that are doing similar types of treatment for this same specific disease, but it's looking really promising. So far they were able to successfully restore, well, at least partial hearing to 10 out of 12 children, they announced during the week. And that's massive. That's massive for a bunch of different reasons. First of all, if you or anyone you know has this type of genetic disorder, fair enough, you can get implants right now, where you can return partial hearing, but this is a potential cure if children have this intervention and it's gets through the rest of the phases of the FDA, and it gets approved. So that's certainly one pro from this. But another pro is it kind of it validates the idea of uh, targeting designing molecules to restore functionality in transmitting information to nerves. And that could have potentially applications, who knows, in the optic nerve or in other types of regions with similar types of inhibiting factors. So really cool story that came out during the week. Kudos to everyone at Regeneron who's working on this. I know some people who work for Regeneron, so it's pretty exciting to see. Um, so yeah, kudos to everyone there. Okay, and the second piece of information or piece of news that came out during the week is this news slapped me in the face like a ton of bricks. It was so exciting. It's possibly my the most exciting piece of news I've seen yet in precision medicine in the last few years. It was the Arc Institute's announcement. And this got a little bit of traction in popular media. It's not often that you see precision medicine getting popular attention. I don't think it got nearly the attention that it deserves, but it did get some piece of media. I'm going to share my screen here now. And it was the Arc Institute, and they announced Evo 2. What is Evo 2? Evo 2 is like the largest AI model that's based on genetic data. So you can treat Evo 2 as one of these. It's similar to an LLM, which is the type of AI model that ChatGPT was built on top of, except it doesn't predict. If those foundational models in the world of LLMs predict, if you give them a list of words, it'll predict what's the next word that it should expect to see given this previous list. Evo 2, you give it a bunch of base pairs, you give it nucleotide data, and if it gets a sequence of these base pairs, it can predict what is the next sequence of base pairs that it should expect to see. Really, really powerful technology. You might think like, well, you're never going to want to chat with base pairs, so it doesn't have the same. You you don't apply this type of AI model in the same way that you would apply a large language model. You're not going to be able to. You don't chat with it, but instead, if you see a list of base pairs and you can predict what's likely to come up next, well, implicitly you've understood patterns in the genetic code of life. You've understood some. This model was able to. It got trained on over 128,000 genomes, so it's read the genetic sequence for over 128,000 genetic sequences. If you imagine these sequences as a book, it's read 128,000 books for various different species in all aspects of life. And from reading all of these books, again, the analogy doesn't exactly hold, it knows how to write a story. And so if you give maybe the parallel here is if you were to give it a sentence, it can tell you whether or not that sentence is structured well or it's structured poorly in a similar way to ChatGPT can help you rewrite your emails. This type of AI model, it can tell you, whether or not a genetic variation is strange or not. It looks suspicious. It's unlikely to have occurred naturally. And there are a ton of applications to this Evo 2 type of model. With the model itself, the Arc Institute have published a couple of things. So they've published a paper that goes through how they built the model and what's going on, how they came about these results, and how they're thinking about it. So it's here, it's up on the archive. They've published the code for this model on GitHub. I think it's on Hugging Face too, and they've got some cool code examples as well. This code example, they were able to use this model without giving it any extra information to predict which BRCA1 variants would be likely to cause loss of function versus which ones were not likely with 90% accuracy. Um, so I would recommend you read this example, which is linked up here on GitHub within the Arc Institute's GitHub release of the Evo 2 algorithm. But this is a pretty cool code example. They took data and they were able to look at the genetic sequence of that data, and based on which genetic sequences they this model has the ability to analyze whether or not it thinks a genetic sequence is likely to have happened or not. And this this code example here, with 90% accuracy, they were able to link unlikely genetics. The more unlikely a genetic sequence is, um, the more likely it is to cause loss of function, which is, if you think about it, like a layer deeper. It's almost like this this code example here reaffirms that from an evolutionary biological perspective, your genetic sequence has some stabilities, and if you deviate too much away from those stabilities, the proteins are going to be defective and they're going to cause loss of function. That makes sense. It's a really interesting paper. They've got a couple of other wrappers above this foundational model. This wrapper here, you can select what organism you're trying to model. You can feed it in with a bunch of base pairs, and I think I have one preloaded here. So I was looking at BRCA1, and I was like, okay, let me select the first. I think it was 500 base pairs. I have that somewhere over here in the spreadsheet, so just so I can copy and paste it easy. And this is a tool that the Arc Institute have just put online for you to just play around with their model. You give it, this is the first 500 base pairs of this particular genetic sequence, and it's going to predict what it thinks the next base pairs to come up are. You can see here TACAGA when this comes up. Okay, this is what we've seen, and then it's TABC, so it's not exact. TATCGAA. So it didn't come up with this one correctly, but that's pretty cool. Um, it's like if you worked with the earlier versions of um OpenAI's transformer models like GPT-2, you can see the direction that this is going. And if you look at how that transformer model evolved and the layers of complexity that were the plugins effectively that were built on top of that, you apply that same thinking here, you can just imagine the amount of different applications this foundation model is going to have. Um, Looking at that same genetic sequence, you can input a genetic sequence and get it to give you a score of how likely this genetic sequence is to occur. In other words, if you have a specific, gene and you want to look at a mutation of that gene, you can input that mutation into this model. It will give you a likelihood score, and according to at least this example, this BRCA1 example, they've given, that likelihood score is somewhat correlated to how how likely that genetic sequence is to result in a loss of function. And that's just looking at input output of the foundation model. There's a ton of other applications that you could apply here. If you know about deep learning, you could think about using the same model, but not accessing the direct outputs, but looking at layers within that model and treating those as embeddings, and maybe doing some cluster analysis on the different layers within this within this model to treat it as a way of creating an embedded space from genetic sequence data. And maybe you want to look at, can you cluster and find sequences of genes or genetic mutations? Can you assess which one is likely to have an adverse reaction to some drug or something like this, just purely based on the embedding space, which is like a middle layer of the model. I don't know. This news story, this was the coolest news story I've come across in a while, which is why I wanted to change the format up for the week. Let me go know what you guys think. I know if you're watching this on Spotify rather than YouTube, it's going to be a little bit trickier to follow. But that's been the news for the week. I know I've got a ton of ideas, and I'm already thinking about ways I can play around with Evo too. If you've come up with any ideas yourself, let me know. Other than that, have a great week. I've been your host, Gary O'Keefe. Ciao, ciao.